Welcome to this part, in which we will put into practice everything that we have learned about wastewater characteristics through an integrated example. You can check all the details in the book Biological Wastewater Treatment, Examples and Exercises, in particular in Chapter 3, Example 3.3. We are going to work with a wastewater treatment plant that is treating the water from a town of 250,000 residents. We know the average daily flow and also the BOD to COD ratio. The plant treats two types of wastewater, raw and settled. When we talk about raw wastewater, we are referring to the wastewater as it is when it enters the plant. On the other hand, we refer to settled wastewater as the water stream after some kind of primary treatment, normally settling, in which part of the solids have been already removed. Therefore, if we compare raw versus settled wastewater, we will expect the settled wastewater to have lower concentrations of suspended solids and also lower concentrations of the rest of the pollutants due to the lower amount of solids. And this is the case if we take a look at the flow-weighted average concentrations of each stream, which are provided in this slide. We have, on the one hand, data on the concentrations of the unfiltered wastewater, both raw and settled. These parameters are total concentrations of organics and nutrients in the wastewater. And these values confirm what we just saw before, that the settled water has lower concentrations than the raw wastewater due to a lower amount of suspended solids. The differences between raw and settled wastewater are the biggest for the suspended solids concentrations, TSS and ISS, followed by the COD and TOC, and then nutrients. We also have information on the concentrations after filtering the sample through a 0.45 micrometer filter. These are then soluble concentrations. In this case, the values are the same for raw and settled wastewater, since the soluble concentrations do not change after primary settling. And only the particulate fractions, so those that can settle, can actually change. We also have information on the effluent concentrations. That means after treatment. We have values of tests performed after treating raw and settled wastewater. We also have additional information, such as the flow of the primary settler tank underflow. That means the stream with the settled solids. We also have information on the particulate and biodegradable COD fraction, and also sludge ratios. And for this case, we can assume that the nitrate and nitrite concentrations in the wastewater are negligible. So we will answer different questions that are related to different concepts that we have seen as part of this course. They are related to population equivalent and person load calculations, also daily and annual flows. We will also do an exercise on BOD and COD removal efficiencies of the plant. We will evaluate wastewater ratios. We will also set up the mass balances over the primary clarifier and also perform the wastewater fractionation. We will assess as well other compounds present in the wastewater, and we will evaluate additional loads as well as perform some hourly calculations. So let's start with the first question. First, we have to determine the population equivalent and person load in terms of flow rate and influent BOD. Let's start by calculating the population equivalent based on daily flow rate. This calculation is based on the assumption that one population equivalent produces 0.2 cubic meter per day of wastewater. With this, we can calculate the number of population equivalents by dividing the daily flow rate by this value. And we can see that the result of the calculation indicates 135,000 population equivalents, which is lower than the number of residents in the city. And this indicates that the wastewater generated is lower than in a typical town. Otherwise, this value would be closer to the number of residents in the city. Now we can calculate the person load based on the flow rate. The person load is calculated as the ratio between the daily flow rate and the number of people in the town. As a result, we get a person load of 0.1 cubic meter per person and per day. Now we have to calculate the population equivalent based on the BOD load. And the first thing that we have to do is to calculate what is the actual daily BOD load. We can do it by multiplying the BOD concentration by the daily flow rate. We don't have the BOD concentration as such from the information that has been given in the exercise, but we know how much is the COD concentration in the influent and also what is the BOD to COD ratio. And with this information, we can first know what is the BOD concentration and then calculate the BOD load. Once we know the load, we can calculate the number of population equivalents by assuming that one population equivalent equals to 60 grams of BOD per day. Then, we can calculate the person load by dividing the daily BOD load by the number of people in the town. So, to sum up, to answer this first question, we have determined on the one hand what is the person load in terms of flow and in terms of BOD. And if we compare the calculated values with the typical ranges, we can see that the person load in terms of flow is within normal ranges, but closer to the lower one. On the other hand, the BOD person load is higher than the normal values. And this is expected since we saw before that the water consumption is low, which means that the BOD concentrations are expected to be higher, and as a consequence, the person load will also be higher. We have also calculated the population equivalents based on fixed conversion values, and we could also draw similar conclusions as for the person load. We observed a flow rate-based population equivalent that is lower than the size of the town, which indicates a low water consumption. On the other hand, the BOD-based population equivalent was higher than the size of the town due to higher concentrations that are associated to the low water consumption. We have answered the first question of this example, so let's go now to the second one on daily and annual COD loads. And for this, we will actually have to calculate what is the daily and the annual COD load of this plant. To calculate a load, which is usually expressed as mass per unit of time, we have to multiply the concentration by the flow. This way, we can calculate the daily COD load by multiplying the influent concentration by the flow rate. And then we can calculate the annual COD load by expressing the daily load in units per year instead of per day. So, by multiplying the concentration by the flow, referred to the different time units, we have calculated the daily and the annual COD loads of this plant. We have completed now the second question, so let's go to the third one. Now we have to calculate the BOD and COD removal efficiencies that are needed to comply with the effluent requirements of the plant, given in this case as BOD and COD concentrations. The first thing that we need to do is to know how we can calculate the removal efficiencies. Normally, the efficiency is calculated as the concentration of the influent minus the concentration in the effluent, divided by the influent concentration. With this definition, and knowing the influent and effluent concentrations, we can calculate the removal efficiencies for both BOD and COD. Note that we can calculate the BOD concentration because we know that we have a certain ratio of BOD-COD of 0.65. In this case, we need a removal efficiency of 94% to comply with the COD limit and an efficiency of 97.5% to meet the BOD discharge requirements. If we go back to the question with the provided information on the influent concentrations and the discharge limits, we were able to determine what are the needed removal efficiencies. So at this point, we have answered 3 questions, and let's move now into the next one about wastewater ratios. We have to calculate different wastewater concentration ratios and compare them with the typical values. We can see in this table all the parameters that we need to calculate all the ratios. And as we can observe, we have the value already for many of them, but a few are missing, and we have to calculate them first before calculating the ratios. So let's start by calculating the BOD concentration. We know that the BOD is assumed to be 0.65 times the COD concentration. And this way, we can calculate the BOD content of the settled wastewater. Next, we have to calculate the total nitrogen concentrations. Normally, total nitrogen equals to the sum of the TKN plus nitrate and nitrite concentrations. However, in this case, we are assuming that nitrite and nitrate concentrations are negligible, and thus we can consider that total nitrogen is equal to the TKN. And this way, we can calculate the total nitrogen concentration for both raw and settled wastewater. Lastly, we have to calculate the VSS concentrations. We know that the total suspended solids are equal to the sum of the volatile plus the inert suspended solids. Since we know the TSS and the ISS, as they are provided by the exercise, we can calculate the VSS as one minus the other. After doing all of these calculations, now we know the concentrations of all the parameters that are needed to calculate the different ratios. And here you can see the results of the calculations for both raw and settled wastewater. And you can also see here as well what are the typical ranges for each ratio. So let's take a look at the values now. First, the COD-BOD ratio, we can see that it falls within the normal ranges, but is closer to the lower threshold. And this indicates that a substantial part of the organics in the wastewater will be easy to degrade biologically. The COD to total nitrogen ratio can be considered medium-high. And this indicates that probably there will be no need to add external carbon source for good nitrogen removal. The COD to phosphorus ratio can also be considered medium-high. Then the BOD to total nitrogen ratio can be considered high, and especially high for the case of the raw wastewater. And this can be related to the high BOD concentrations that we discussed before due to a low water consumption. And the same conclusion can be also drawn for the COD to total phosphorus ratio that also has high values. The COD to VSS ratio can be considered very high and slightly above the typical values, especially for the case of the settled wastewater. In this case, the value of the settled wastewater is higher than the raw wastewater, probably due to the lower suspended solids concentration. The VSS to TSS ratio can be considered high, which indicates that a big fraction of the total suspended solids is organic, and this could be, for example, successfully digested under anaerobic conditions. And finally, we have COD to TOC ratios that can be considered medium-high. So going back to the question, we have calculated all the ratios, and for this, we have to calculate first some missing concentrations based on ratios or assumptions that were provided in the exercise. And in general, we saw that most of the ratios were within the normal ranges. So up to this point, we have completed 4 out of the 9 questions of the exercise. Let's go now to the next one, in which we have to set up the mass balances over the primary clarifier. And here you might wonder, how do I set up a mass balance? Well, to do that, the first thing that we have to do is to look at the flow diagram of our unit process. In this case, we have a primary settling tank, and we have 3 streams involved. We have 1 incoming stream, which is the raw wastewater, and 2 outgoing streams, being the settled wastewater that goes out at the top of the settler, and the underflow or primary sludge that goes out at the bottom of the settler. Each stream has their own flows and concentrations, and this is what we have to calculate with mass balances. To set up the mass balances, we normally start with the balance over the volumetric flows, and then as a second step, we do the same for the mass flows of the individual components. So let's start with the volumetric flow rates. We know from the information given in this example what is the flow of the raw wastewater. And we also know what is the fraction of the wastewater that will go out in the primary sludge stream. And if we know this fraction, we can calculate what is the actual flow rate of the primary sludge. And this is basically all that we can calculate with the information given in this example. And at this point, the only thing that is missing is the flow of the settled wastewater. And this we can calculate it through the mass balance. That means that we can calculate it as the difference between the raw wastewater and the primary sludge flow. We can estimate the settled wastewater flow this way because we are assuming that the principle of conservation of mass is followed. And after this step, we have completed the mass balance over the clarifier in terms of volumetric flows. Now we can calculate the individual components' mass balances. And to do this, we have to estimate the mass flow rate as the product of the volumetric flow rate and the concentration of each component. For example, in this slide, you can see how the COD mass flow rate is calculated. And for this, we just multiply the incoming flow by the COD concentration. We can do the same with the settled wastewater, since we also know the flow and the concentrations. And at this point, the only thing that is remaining now is the mass flow of the primary sludge. We can calculate this as the difference between the mass flow rate in the raw and the settled wastewater. And we can do this for COD and other variables as well, as long as their mass is conserved over the primary clarifier. This means they have to be conserved quantities. And this is definitely the case for COD, total nitrogen, and total phosphorus. And it applies as well to TOC and suspended solids, since they do not undergo any transformations in the settler. Once we know the mass flow rate, we can calculate the concentrations in the primary sludge stream by dividing the mass flow rate by the volumetric flow. And we can basically apply this calculation procedure for all the different parameters. And here you have the results of the mass balances for all the different components. And here there are some things that we can extract from the results. First of all, the primary sludge stream has a much lower flow rate than the raw and the settled wastewater. On the other hand, the concentrations of this primary sludge stream are much higher than the other two streams, since the primary sludge is mainly constituted by settled solids. In the end, if we look at the mass flow rates that are calculated as the product of the flow and the concentrations, we can see that they are in the same order of magnitude for the three streams. We can also see from the values of the mass flows that almost 50% of the total suspended solids from the raw wastewater end up in the primary sludge, while the rest remains in the settled wastewater. In particular, an even higher fraction, 66% of the inert suspended solids, also ends up in the primary sludge. And this value is higher than for the total suspended solids because the inert suspended solids are normally more easily separated in the settler compared to the volatile suspended solids. On the other hand, we can also see that 35% of the organics ends up in the primary sludge, while the rest remains in the settled wastewater. And finally, around 20% of the nutrients are separated in the primary sludge, while the rest remains in the settled wastewater. These values are lower than those of the organics, since the particulate fraction, which is actually removed by settling, is lower for the case of the nutrients. Going back to the initial question, we have set up the mass balances by starting from the flow diagram. And we set up the mass balances for the volumetric flows first, and then for individual components. And we can apply this principle as long as the components that we are considering are conservative. Let's go now to the next question on wastewater fractionation. Here we are going to characterize the COD, nitrogen and phosphorus fractions of three different streams. And for this, we have to apply the calculation procedure for the fractionation of each variable that we have seen before. Let's start with COD. This is the scheme that we will use as reference for the calculations. The COD here is divided on the one hand into a soluble and a particulate fraction. And on the other hand, we can also divide it into biodegradable and non-biodegradable. And this results in four different fractions that we have to calculate. So let's follow the procedure with raw wastewater as an example, but it is basically the same for the other streams. As first step, we know the total COD concentration from the information given in the example. As second step, we also know what is the soluble COD concentration, also given by the exercise. Then we can calculate the particulate fraction as the difference between the total and the soluble COD. Then we can calculate the unbiodegradable soluble COD by assuming that it will be equal to the COD concentration in the effluent. Here we are basically assuming that the plant is able to remove all the soluble biodegradable COD, and what is left is only the unbiodegradable fraction. Once we know the soluble COD and the unbiodegradable fraction, we can calculate the biodegradable part as the difference between one and the other. By the end of this step, we have completely characterized the soluble COD fractions. So let's go now into the particulates. Now we can calculate the particulate unbiodegradable fraction by considering the sludge ratio that has been provided in the example, which is 0.15 grams of unbiodegradable COD per gram of total COD. And we can calculate the concentration by multiplying this fraction by the total COD concentration. We can apply this calculation to estimate this fraction for both raw and settled wastewater. In the case of primary sludge stream, we cannot apply this calculation since we don't know how much this fraction of unbiodegradable organics is. But what we can do instead is to estimate the concentration from the mass balances, as we did before. Then, the only fraction left is the biodegradable particulate organics, which can be calculated as the difference between the particulate and the particulate unbiodegradable COD. After completing this calculation, we have completed the whole characterization of the different COD fractions. And here in this table, you have a summary of all the different values for the three streams that we are considering. We can observe on the one hand that all the soluble compounds have the same concentrations in all the streams. And this is because they do not undergo any transformations in the settler. Also, we can observe lower concentrations of the particulate fractions in the settled wastewater compared to the raw wastewater, as a result of the separation of the solids in the settling tank. Compared to the raw and settled wastewater, the primary sludge stream has a much higher particulate concentrations and also a much higher total COD concentration. So with this, we conclude the COD fractionation, and let's go now into the nitrogen fractionation. Here we start with a similar scheme as basis. We can divide the total nitrogen concentration into two fractions, free saline ammonia, or FSA, and organic nitrogen. Since the inorganic nitrogen in the form of nitrate and nitrite is typically negligible, we will not consider it in the calculations. The organic nitrogen can be further subdivided similarly to COD. On the one hand, we will have a soluble or a particulate fraction, and on the other hand, we will have a biodegradable and unbiodegradable fraction. So let's go now again step by step, using also raw wastewater as an example. As first step, we know what is the total nitrogen concentration that we assume to be equal to the TKN. We also have information on the soluble TKN, and this is equal to the sum of the ammonia and the soluble nitrogen fractions. The next step consists of the calculation of the particulate nitrogen as the difference between the total and the soluble. We also know from the example what is the concentration of the free saline ammonia or ammonium concentration. And then with this information, we can calculate the soluble organic nitrogen as the difference between the soluble TKN and the ammonium concentration. We can now calculate the soluble and biodegradable nitrogen by assuming that it is the same as its concentration in the effluent. We can know the effluent concentration by calculating the difference between the soluble TKN and the ammonia concentration. Now we can calculate the amount of soluble biodegradable nitrogen as the difference between the soluble TKN and the ammonia and unbiodegradable nitrogen. At this point, we only have the particulate fractions left to calculate, and we can start by calculating the particulate and biodegradable nitrogen by taking into account the nitrogen fraction of the particulate and biodegradable COD, or FN, and this information has been given in the example. It is important to always pay attention to the units. In this case, the nitrogen fraction was given as a function of the volatile suspended solids. This means that we have to convert the unbiodegradable organics into the same units, And that is why you can also see in the calculation the ratio FCV, which is used to correlate the COD and the suspended solids. Finally, we can calculate the amount of particulate biodegradable nitrogen as the difference between the particulate nitrogen and the particulate unbiodegradable nitrogen. And with this calculation, we have finished estimating all the nitrogen fractions from the wastewater. In this table, you can see a summary of all the different numbers corresponding to the three streams that we are considering in this exercise. And again, we can draw similar conclusions as those from the COD results. We can see on the one hand that the soluble concentrations are equal for all the streams. And then we can see that the particulate fractions are the highest for the primary sludge, followed by raw and then settled wastewater. Let's start now with the calculations for the phosphorus fractionation. Similar to nitrogen fractionation, we can divide the total phosphorus into an inorganic fraction, orthophosphate, and an organic phosphorus. The organic phosphorus can be further divided by considering on the one hand the soluble and the particulate fractions, and on the other hand the biodegradable and unbiodegradable fractions. Again, we will do this example with the numbers for the raw wastewater, but the calculations are the same for the three streams. First, we know how much is the concentration of the total phosphorus since it has been given by the exercise. We also know what is the concentration of soluble phosphorus because it has been also given by the exercise. This concentration corresponds to the sum of the inorganic phosphorus or orthophosphate plus the soluble organic phosphorus. The next step consists of the calculation of the particulate phosphorus concentration as the difference between the total phosphorus and the soluble phosphorus. This concentration also includes both the biodegradable and unbiodegradable phosphorus. We also know from the exercise what is the concentration of the orthophosphate. And with this information, we can calculate the amount of organic phosphorus as the difference between the total phosphorus and the inorganic phosphorus. This organic phosphorus concentration is the sum of the four organic fractions. We can also calculate the amount of soluble phosphorus as the difference between the total phosphorus and the particulate phosphorus and the inorganic phosphorus. Ideally, we would need to estimate as well the amount of soluble and biodegradable phosphorus the same way as we did for nitrogen and COD. And this would mean calculating its concentration based on the effluent concentration. However, we do not have enough information for this, and therefore we cannot further estimate the soluble fractions of phosphorus. Nevertheless, we can still estimate the fractions of the particulate compounds. We can start with the unbiodegradable particulate phosphorus that can be again calculated by using the phosphorus fractions of the unbiodegradable particulate COD that have been given by the exercise. Again, it is important to pay attention to the units during these calculations. As last step, we can estimate the particulate biodegradable phosphorus as the difference between the particulate concentration and the particulate unbiodegradable concentration. And after this step, we have finished all the calculations for the different phosphorus fractions. And here in this table, you can see a summary of all the numbers corresponding to the three streams that we are taking into account for this exercise. And again, we can draw similar conclusions as for COD and nitrogen. We have on the one hand the same soluble concentrations for all the streams, And we can observe differences regarding the particulate fractions. The concentrations are the highest for the primary sludge, followed by raw and then settled wastewater. So, going back to the question, we have characterized each streams in terms of COD, nitrogen and phosphorus fractions. And to do that, we have calculated each concentration by using information from the exercise and using as basis the schemes that are shown in the slide. Let's move now into the next question of this exercise, in which we will focus on evaluating the concentrations of other compounds. And for this, we have the following information. We have the values of the concentrations of different sulfur compounds in the raw wastewater, including sulfate and sulfide. We also know the concentrations of cellulose in the raw wastewater. We also have information on the concentrations of different toxic compounds, including polycyclic aromatic hydrocarbons, or PAH, linear alkylbenzene sulfonates, or LAS, phthalates, or DEHP, and nonylphenols, or NPE. We also know the concentrations of different metals in the raw wastewater, as well as the removal efficiencies of the plant. And we also have information on the concentrations of 3 different microorganisms, as well as the removal efficiencies of the plant, expressed in different units, including normal percentages and LRV, which refers to the logarithmic removal value. And here we will answer 3 sub-questions. First, we will analyze the concentrations of different compounds. Second, we will evaluate the need for additional treatment for metals in order to comply with certain plant discharge limits. And third, we will assess the possibility of water reuse based on the microorganism's concentration. So let's start with the first sub-question. Here we have to see if the provided concentrations are typical or not, and that means if they fall within the normal ranges for municipal wastewater. So let's start with sulfate and sulfides. In this table, you can see the typical ranges for these compounds in municipal wastewater, as well as the concentrations for this specific case study. For both compounds, the concentrations are within the typical values, being medium-high for the case of sulfate and medium-low for the case of sulfide. Regarding cellulose, we know that the typical range should suppose a 20–30% of the COD load and around 35% of the TSS load. In this example, we have a cellulose concentration of almost 300 milligrams per liter. And if we calculate the ratio between this value and the corresponding COD and TSS concentrations, we can obtain a 23% of the COD load and a 38% of the TSS load. In both cases, these values fall within the typical ranges, and they can be considered medium-high values. If we take a look now at the toxic organic compounds, we can see here again the concentrations corresponding to the typical values and also those corresponding to this case study. And we can see that also in this case, all the concentrations fall within the normal ranges and they could be considered low or medium. And here we can evaluate the metals concentrations. We can compare the typical range with the concentrations for this case study. And we can see again that all of them fall within the typical values and they could be considered medium or high depending on the specific metal. So to answer this first question, we have compared the concentrations of this study with the typical values from municipal wastewater, and we can say that all the evaluated concentrations fall within the normal ranges. Let's go now to the next question, which focuses on evaluating the need for additional treatment of metals. Let's assume now that the plant is located in Europe and it has to comply with the emission levels that you can see in the slide in terms of metals. We have to analyze if we need additional treatment for the metals if we want to comply with these regulations. For this purpose, the first thing that we need to do is to calculate the effluent concentrations. And we can do that by taking into account the removal efficiency for each metal, which is provided in the example. In this table, you can see a summary of the removal efficiency for each metal, and also what would be the associated effluent concentration after the calculations from the previous slide. And we can compare this value with the discharge limit. And we can see that in all the cases, the effluent concentrations are much lower than the effluent requirements, and this means that additional treatment is not needed. So, to answer these second sub-questions, we have evaluated if additional treatment was needed or not for metals to comply with the discharge limits. And to do this, we calculated the effluent concentrations based on the provided removal efficiencies, and we observed that all the concentrations were below the limits. So, additional treatment was not needed. Let's go now to the next question regarding the microorganisms concentrations. Here we have to evaluate if the effluent of the wastewater treatment plant could be reused for agricultural irrigation in terms of microorganisms concentrations. And in order to know this, we can use as basis the information from this slide, which provides the criteria to classify the reclaimed water based on the concentrations of Escherichia coli, BOD, TSS, and turbidity. We can see that we have 4 different types of reclaimed water based on the Escherichia coli concentrations. Let's assume for this case that the water complies with the requirements regarding BOD, TSS, and turbidity, and let's pay attention only to the microorganisms concentrations. Here we have additional information on the reclaimed water related to the final use based on its quality. We can see different crops categories and also what is the minimum water quality that is needed for the irrigation of these crops. The water quality is presented following the same classification as we saw in the previous slide. And we have information as well on the allowed irrigation method. If we want to know in which situations the water could be reused, we first need to calculate the effluent concentrations of the different microorganisms. And to do that, like for the metals, we have to estimate the effluent concentrations by taking into account the removal efficiencies, which are also provided in the exercise. And to do this, we have 2 different ways to calculate the effluent concentrations, and they depend on how the removal efficiencies are expressed. For the case of the Escherichia coli and Legionella, the removal efficiency is given in terms of a logarithmic removal value, which equals to the logarithm of the influent concentration divided by the effluent concentration. And we can calculate the effluent concentration by rearranging this equation. For the case of the Helminth-X, we have information on the removal efficiency already expressed as a percentage. So we can use the same calculation methods as in previous examples in order to know how much would be the effluent concentration. And here we have the results of the calculations. If we compare these concentrations with the limits provided before, we can see that based on the concentration of Escherichia coli, we can classify the water as Class C reclaiming water. And we can also see that the concentrations of both Legionella and Helminth-X are below the limits. Based on these effluent concentrations, we can reuse the water for food crops that are consumed raw, where the edible portion is produced above ground and is not in direct contact with reclaimed water. And we can also use the water for processed food crops and also for non-food crops, and this includes crops to feed milk or meat-producing animals. So to sum up, as part of this question, we have answered 3 sub-questions. First, we compare the concentrations of different compounds with the typical ranges observed in wastewater. And we saw that all of them were within the normal concentrations. Then we evaluated if additional treatment was needed for metals to comply with the discharge limits. For this, we calculated the effluent concentrations based on the provided removal efficiencies, and we observed that all the concentrations were below the limits, so additional treatment was not needed. And finally, we evaluated the potential water reuse for agriculture based on microorganisms concentrations. And to do this, we also had to calculate the effluent concentrations, and we compared their values with the reclaimed water criteria. We saw that it was possible to reuse the water, and we classified the water as water quality class C, that has certain applications. Let's move now to the next question, in which we have to evaluate additional loads. Imagine that now a factory plans to discharge a certain amount of wastewater with a certain BOD into the sewer that goes to the treatment plant of this case study. We know that the plant can handle maximum 50% more than the current BOD load that is being treated in the plant. To evaluate this additional load, we will have to answer 4 questions. First, we have to determine if the BOD concentration is realistic or not, and then we have to make some calculations associated to the discharge that will include the maximum discharge flow rate, the minimum time needed for the discharge, and the dilution factor. Let's start with the first sub-question, in which we have to see if the BOD concentration is realistic or not. And in order to do this, what we can do is to calculate the BOD concentrations and then compare it with the typical values of different wastewaters. To calculate the BOD concentration, we have to divide the mass of the BOD by the volume of the wastewater. We already have both numbers from the exercise, and we can calculate a concentration of 20,000 grams of BOD per cubic meter. This is quite high if we compare it with municipal wastewater that normally has less than 500 grams per cubic meter of BOD. Nevertheless, it is within the realistic ranges if we think about industrial wastewater instead. In particular, it would be within the ranges of the typical concentrations for greenery and dairy wastewater. Thus, we can say, to answer this question, that indeed the BOD concentration that we are considering is realistic. Let's go now to the second sub-question, in which we have to calculate the maximum discharge flow rate of this concentrated stream, taking into account that we have to reduce the risk of potential process disruptions in the plant. If we want to make sure that there are no problems of process upsets, we have to ensure that the extra BOD load will always be below the maximum capacity that the plant can handle. And in this case, we are talking about 50% more than the current capacity. We know from previous calculations in this exercise what is the current BOD load that we have. And we can calculate how much would be the maximum BOD load that the plant can treat if we multiply the current load by 1.5. And why do we do this? Because then we are taking into account that extra 50% that the plant can still treat without additional problems. Once we know the maximum load, we know that the extra load that can be treated in the plant will correspond to the difference between the maximum and the current BOD load. And this result gives us a maximum additional load of 457 kilograms of BOD per hour. If we know what is the maximum load that we can add as an extra, and we also know what is the BOD concentration of the wastewater, then we can calculate what would be the flow corresponding to this extra discharge. And after this calculation, we know that we can discharge around 23 cubic meters per hour, and the plant will still be able to handle it without problems. So to answer this question, we have calculated what would be the maximum discharge flow rate by taking into account the concentration of the wastewater and the extra load that the plant can handle. Let's go now to the next question. Now we have to calculate the minimum time that is needed to discharge the entire volume of wastewater. We can calculate the minimum time needed by dividing the volume of the wastewater by the maximum flow that is allowed to be discharged without implying potential issues in the plant. And with this calculation, we obtain a minimum duration of the discharge of around 2 hours. So to answer this question, we have calculated the minimum time needed for the discharge by considering the volume of the wastewater and the maximum flow rate that we calculated before. Let's move now into the last question, in which we have to calculate the corresponding dilution factor of the concentrated wastewater. This means that we want to know how many times the flow rate of the wastewater coming to the plant is higher than the concentrated wastewater flow that we are adding as an extra stream. To do this, we can calculate the dilution factor by dividing the wastewater flow by the flow of the concentrated wastewater. After this calculation, we get a dilution factor of 49, which basically indicates that the flow of the wastewater that is coming to the plant is 49 times higher than the flow of this extra concentrated stream. So to sum up, in this part, we have answered some questions about additional loads. We considered an extra discharge from a factory, and first we had to determine if the concentration of the wastewater was realistic or not. We saw that it was within the ranges of the typical industrial wastewater composition. Then we had to calculate the maximum discharge flow rate to avoid process disruptions in the plant. And to do that, we took into account the maximum BOD treatment capacity of the plant, as well as the additional load that could be added with this stream. And with this, we determined a maximum flow rate of around 23 cubic meters per hour. Then we calculated the minimum time needed to discharge this concentrated wastewater by taking into account the maximum flow rate calculated in the previous question. So now we have completed almost all the questions, and let's go to the last one, in which we have to do hourly calculations. We know that the concentrated wastewater is mainly received between 7:30 in the morning and 6:30 in the afternoon. And based on this time, we have to calculate what could be the maximum hourly flow rate and the maximum hourly constant. For this, the first thing that we have to do is to calculate the hourly factor. That means the time window in the day in which the plant actually receives the wastewater. We know that it is between 7:30 in the morning until 6:30 in the afternoon. That means that we have 11 hours per day in which the plant is receiving the concentrated wastewater. We can then calculate the maximum hourly flow rate by dividing the sewage wastewater flow by the hourly factor. The maximum hourly constant is defined as the ratio between the maximum and the average hourly flow rate. And we can calculate this just by dividing these two values and taking into account that we have to use the correct units. And we obtain a value of around 2, which indicates that the maximum flow rate is around 2 times higher than the average flow rate. And this makes sense since the hourly factor is 11, which is a bit less than half of 1 day. So it makes sense that then the flow is 2 times higher than the average flow. So to answer this question, we have calculated the maximum hourly flow rate by considering the time window in which the wastewater is received. And we have calculated the maximum hourly constant by dividing the maximum flow rate over the average flow rate. So at this point, we have completed all the questions of this exercise. We have considered, for this case, a specific wastewater treatment plant, and we have answered different questions related to all the aspects that we have seen in this chapter on wastewater characteristics. First, we gave an impression of the wastewater load applied to the plant by calculating the population equivalent and the person load. Then, we calculated the daily and annual COD loads of the plant. Afterwards, we calculated the removal efficiencies that were needed to comply with the discharge requirements for certain compounds. We also calculated different wastewater ratios and we assessed their values. Then, we set up the mass balances over the primary clarifier of the plant. And we also made calculations on the wastewater fractionation of the different COD, nitrogen, and phosphorus fractions. And we also evaluated the concentrations of other compounds, such as sulfur or toxic compounds, and also metals. And we also evaluated the possibility of water reuse, taking into account the microorganisms concentration. Then we consider a case of an extra discharge of a concentrated stream into the plant, and we made some calculations on the discharge requirements. And finally, we made calculations as well related to the hourly flow rate and the hourly constant.